Here's a challenge for you. Flick this card from under the coin, but make sure that this coin doesn't drop into the glass. Sounds simple, right? Think you can do it? Let's see. I bet you can't pull it off. The coin fell into the glass. Let me show you why this is harder than it seems. This trick is all about inertia. While the card moves away, the coin stays at rest due to its resistance to motion. That's inertia. Want to learn more? Let's dive deep. But students, before we start, don't forget to like, share and subscribe to our channel. Let's learn together. Hello students, welcome in today's class. So today we are going to begin with the new unit of physics, which is forces and motion. Alright, so you are understanding what are we going to learn today. So we are going to talk about first forces and secondly how forces affect motion. Since motion we have already studied in the previous unit. So we are not studying motion now, but what we are going to study is how forces affect motion or cause motion. Because again I want to remind you one thing. In the last chapter when we were discussing motion, I precisely told you that we are going to study motion, but we will not talk about its cause. And today we will start with that cause. Keep that in mind. Alright. So before we even begin with this unit, the first thing that I would ask you that if you talk about forces, how do you define force? Since this is not something that you have not ever heard of, you definitely have heard of force as a term and maybe you also know the basic definition. Let me keep it very simple for now, that a push or a pull is called a force, right? So this is how you would imagine a force, a push or a pull, that is a force. That definition is even valid in this particular class, that a push or a pull is simply a force. Okay. Second thing that I wish to talk about before we start with this unit is that force is a vector quantity. Force is a vector quantity. So if you remember in the previous unit we have talked about how physical quantities are of two types. Either they are scalars where only the magnitude is important, or they are vectors where the magnitude and direction both become equally important. So force is something where the direction of applying force is definitely something which is very important, and therefore force is a vector quantity. Third thing that I wish to talk about is that its SI unit. Its SI unit, I don't know if you have ever heard of this, but is Newton, denoted by uppercase N, okay, is Newton. So SI unit of force is Newton. So these are the three preliminary things that you should know before we begin or dig deep into this unit. So what is this unit about? Forces and motion. Alright. So just make a brief note of this. Put down the name of the chapter, the heading as the name of the chapter, and just write these three simple facts about force. I will wait. Alright, so you've copied it down, you pause the video and copy it down. Next what do we wish to talk about? So a lot of things. First thing, various facts about forces is what I am going to talk about. Second, Newton's laws of motion. Alright, Newton's laws. So Newton, of course you have heard the name of the great physicist Newton, Sir Isaac Newton. So he obviously the governing, or let's say the the guiding light of this entire unit of mechanics is governed by the Newton's laws of motion. So these are the most fundamental laws that are going to govern the physics that we are going to proceed with. So Newton's laws are very important, we'll talk about them. Again, adding forces. Keep one thing in mind, we already have talked about adding vectors. So when I say adding vectors, adding forces is just a category of that only. In fact, all the discussion that we've had about vectors, that was in context of forces only. So adding forces is something that you already have a preliminary idea about. Alright. Then we talk about types of forces. What are the various types of forces? That is also something one by one we will talk about. but not maybe all of them together, but some of them in this particular unit. And as we proceed, we will talk about the other forces as well. Mass, weight and gravity. Mass, you already have an idea of what mass is. Amount of matter, we are going to discuss that. Gravity, you do understand that anything if dropped falls under the influence of gravity. And then is the weight. Okay, weight is also something that we are going to discuss in detail, but I am not doing that right now and making things complex for you. Next is force, masses and acceleration. How these three quantities, force, mass and acceleration, are closely knit or closely related with each other. They have infinite love for each other. Force, masses and acceleration. We'll understand how. Next is momentum and impulse. Okay, so that is also a quantity that is related with force. So we are going to discuss those quantities as well. You can again briefly note down all these quantities or these headings and then we move forward. All right. So next thing, what changes can force make? Okay, what changes can force make? So when you apply force on anything, you can just imagine pushing someone, all right, or pulling someone. What changes can you think you can make? What, how would the motion of anything would be affected when you apply a force on that? Let's talk about that, and it's very basic, you can understand. Okay, so one by one I have the diagrams with me just to elaborate on what I am saying. Okay, so the first thing is you expect a change in speed. Okay, so let's have this simple situation. The car is already moving forward, that is to the right, and you then further apply a pushing force to the right. Just forget about physics, think in very general manner. Then you would say that of course when you are applying the force, you are supporting the motion of the car and hence its speed should increase, the motion amount should be increasing, and that is what we expect, that if the force applied is in the same direction as motion, then its speed is going to increase. On the contrary, imagine if the car was moving forward and you are pulling it backwards, you just imagine that it's not that powerful of a car. Otherwise you would obviously you get carried away with the car, but let's assume that you are energetic enough or powerful enough to apply a sufficient amount of force. So what do you expect to happen? Obviously the motion of the car is going to get hampered, or you would say it will suffer a deceleration. So can we say this force is kind of a situation of acceleration and this force is kind of a situation of deceleration? So the first thing that you should understand is that force can change speed. So it can bring about a change in speed. Next thing, you can also expect a change in direction. All right, you can also expect a change in direction of motion. So you can have n number of examples. All right, so for that as well. So for example, if a ball is thrown towards you and you hit it with a bat, okay, or a tennis racket, what have you done? The ball was already in motion and you hit it in some other direction. So by applying a force, you have changed its direction. So that is very obvious, you can understand, you can bring about a change in direction of motion. Okay, so this is done, you do understand that, and this is also very obvious. The third thing is, which we are going to study in the later half of this chapter, is that you can also expect a change in shape or size of any object by applying a force. So for example, you have this paper and then you crush it or you twist it or whatever you may call it. When you crush it, the paper is still at rest. Okay, it was in your hand, you crush it, it is still at rest. Okay, it has not changed its direction as well. But then what have you done? You have entirely changed the shape or the size or the arrangement of the solid. Okay, so you can also expect a change in shape. So just with that thought that these are the three different ways in which force can affect things or motion, I think we can move forward. So keep that in mind. Just one line phrase about what changes can force make. First, change in speed, second, change in direction, and third, change in shape. Please write it down and then we move forward. So I hope you're understanding. We are doing the basic vocabulary today so that we are in a state to learn the chapter in detail and also do the associated numerical problems. So today we are doing the basic vocabulary so that that foundation is there, and then we can, you know, think of constructing a building over it. All right. Please note these down and then I'll move forward. Okay. Next thing, force and acceleration. All right. So what are we talking about? Force and acceleration. So as I was telling you that there is close relationship between force and acceleration. Somehow you do understand that in the previous example also, by applying force you were either causing an acceleration or deceleration. So who's the root cause of that? Who causes acceleration or deceleration? The answer is going to be force. Force is the root cause of that. So let's understand, you know, taking a lot of examples very quickly to, you know, have that feeling of what exactly force can do. So I have an example here. The car is moving with a speed of 2 meters per second and you apply a force, and that is a case of speeding up because the force is applied in the same direction, okay, and therefore the speed increased. Okay, to slow down the car, of course the force has to be applied in the opposite direction. Okay, so I am showing here that the force is applied, but of course the force is applied in the opposite direction, and then also, you know, it can cause a change in speed, but this time it is a decrease in speed. So when force and velocity are in same direction, you expect an increase in speed, and if force and velocity are in opposite direction, you expect a decrease in speed, obviously. Okay, now again, so these were already in motion and brought to another state of motion, but here what is happening? This car is at rest. Understand, car is at rest and you want to bring it in motion. Even then you need a force. Even then you need a force. Okay, so to bring any body in motion from the state of rest, what you need is a force. Okay, so imagine yourself, if you are at rest, you are sitting somewhere, you are standing somewhere, you want to move forward. What do you expect? How can you move forward? There's only one way, that you move forward by experiencing a force from the ground. We'll talk about that in detail, but if you want to move from rest, you need force. Okay, next, to stop an object. Now vice versa of that, you are in motion and you say we apply brakes to stop the car. Now what are the brakes doing? They are giving you a braking force. They are causing a deceleration, sure, but that's a braking force. That force experienced by the car is ultimately, you know, making the vehicle stop. So to stop an object, again we need a force. So is it going to your head that, you know, you need force whenever you want to change the motion? Let's keep it very simple by looking at these 4 examples, that you need force if you want to change the motion. You need force for that. Okay, then this is a little surprising because you might wonder, to keep an object at rest, there is no need of force. Okay, so there is no need of force to keep an object at rest. Of course, if something is at rest, you know, you do understand that this is something you have studied in your previous classes. You don't need anything. It can remain at rest. There's no, you know, external agency needed there. An object will remain at rest, in fact, unless there is a force. So there is no force to keep an object at rest. You don't need a force. And to your surprise, if I say that this car is moving, does it need force? The answer is surprisingly no. To keep the car in motion, you don't need force if that motion is being maintained. So here the velocity of the car is 4 and this is again 4. Is it changing? Is the magnitude of velocity changing? No. Is the direction changing? No. So there is no change in anything whatsoever. Do you need a force then? No. To keep this car in motion with that same speed, you don't need force. Think about a meteor. It has been traveling from hundreds and thousands of years, let's say. Does it need a force to keep moving? Answer is no. If it is moving, it will keep on moving. There's no need of force. So don't always assume that, you know, force is something that is needed to cause motion. Yes, it is true. If you are starting from rest, you need force to bring it in motion. But if it's already in motion, no force is needed. It will keep moving. Okay. So force, if you want to, you know, understand something after these 6 examples, you just keep one thing in mind. Force is needed if you want to change the motion. I'll say that again. Force is needed if you want to change the motion, alright. Otherwise, if the state of motion is to be maintained, force is not needed, okay. So, you will understand what I am saying as we proceed with the Newton's laws, but for now you can just make a quick note that for causing change in velocity, acceleration or deceleration, we do need force, okay. Write that down, this particular line, and then we move forward. Alright. The next thing, types of forces. So, I am not discussing this in detail right now, it's not needed at all. This is the whole study of physics. One by one we will understand each and every force in detail. I just want to name the forces for now, and with time you will understand that what these forces are, how they operate, what changes they can bring about. First is weight. Just to give you an idea, weight is the pull of the earth. So, if I am releasing this pen, okay, and this is falling, then you will say that it is the force of gravity is the weight basically, okay. Contact force, imagine force of gravity is also acting on me. Why am I not falling then? Why am I not falling? You would say because you are standing on the ground. You are standing on the ground. So, if you are standing on the ground, what is going to happen? The force of gravity is here and there is going to be a contact force, a normal contact force from the ground that is stopping me from falling. You can call it like that. So, contact force, anything. So, for example, this pen, if I am pushing this pen, so this force being applied by me is obviously contact force, okay. Next is tension. Tension, you do understand, any rope, you think of any rope, it might be slack, right, it might be relaxed, you can say, but when you make it taut, you apply a force, then there is a force developed in the string. That force is called tension force, okay. So, by developing tension, you can pull something. Imagine you tie the rope to a box and then you pull the box. So, what are you doing? You are building up tension in the rope, and that tension in the rope is pulling the block, understand, okay. Frictional force. So, we will study friction in two parts, one related with solids and one related with liquids or gases, okay. So, when I say solids, any car moving on the road is giving some resistance to the motion, you can call it like that. That force is basically friction. So, friction is something that you will understand later, but for now I would just say frictional force is a force that opposes relative motion, alright. So, any force developing like this, even like this, is frictional force. In fact, it also dissipates or produces heat. That is also something which is very important and we are going to discuss. Next is spring force. You understand what a spring is, okay. So, the force applied by a spring is therefore called a spring force. So, we will discuss that. It is a very special topic, we will take it in detail. Next is drag force. So, as I was saying, when friction is experienced in fluids, so when I say fluids, I mean liquids and gases, anything that can flow, then that is called drag force, okay, or air resistance. So, imagine when the car is moving, it is not only experiencing the frictional force due to the ground, but when it is moving through the air, it is also experiencing a drag force due to the air or the air resistance, okay. So, keep that in mind. Next is upthrust. I will talk about that. So, when you are in any water body like a swimming pool or a lake, something of that sort, then you do feel lighter, you do feel a force in the upward direction due to that liquid, that is hence called upthrust, okay. Next is electric force. You understand, force between charges. Magnetic force, force between magnets, and then there is nuclear force as well, which we will discuss very later on, but you should understand it is somewhat a force inside the nucleus, alright. So, that's all about the types of forces. I don't want to dig deep into these topics, I just wish to name the forces, types of forces. You can just briefly write them down or take a screenshot of this. Otherwise, also we are going to share the slides with you or the link where you can get these slides so that you can easily refer these after whenever you need them for revision. But still, if you want to copy this down, just pause the video and write it down. Alright. So, next thing, resultant force. So, this is something we have already talked about, when we were talking about adding vectors, but right now I just want to take a couple of examples just to understand how, you know, forces add up. And when I use the word resultant force, that obviously means the overall effect of force that is that someone is going to experience. All right. So a single force that has the same effect on a body as two or more forces combined, that is what you call resultant force, of course. Now I have a couple of examples here. You know, first example, there are two persons applying a force of 200 Newton and 300 Newton, and it's very simple, both are applying the force in the same direction. What is the net force this block will experience? The answer is going to be, of course, 500 Newton, alright, because 200 and 300 is going to add up to become 500. On the contrary, now think of this, when one person is applying 300 Newton here and the other person is applying 200 Newton here, what is the net force that the block is going to experience? So you would say, sir, they are acting in the opposite direction, and probably the net force is going to be the subtraction of the two, and that is going to be 100 Newton. Yes, that is going to be 100 Newton. So that is something that you can think of, at least when the vectors or the forces are either in same direction or in opposite direction. So if they are in same direction, the net force is addition of the two, and if they are in opposite direction, then the net force is the subtraction of the two. But one more case that I wish to talk about, which you are not seeing here. What if this person also applies a force of 300 Newton? Okay, then this is 300 and this is also 300. What do you think the net force is going to be now? The answer should be 0. The answer should be 0, because 300, 300, you subtract the 2 and you get a 0. Understand, this situation of 300 and 300 is called a situation of balanced force. So we say that yes, forces are acting on the block, but they are balancing each other off, and the net force is going to become 0. The net force is going to become 0, and there won't be any net effect of force. Keep that in mind. Okay, so 300 here, 300 here, this is balanced force. But if it was 300 and 200, then that is called unbalanced force. What is that called? Unbalanced force. So when you have unbalanced force, you feel a net force, and that is when you feel the effect of force. This is also unbalanced, there's no doubt about it, because both are acting in the same direction. They are not balancing each other off for sure. So 200 and 300, this is of course an unbalanced force of 500. This is of course an unbalanced force of 100. But if it is 300 and 300, then they are called a pair of forces which form balanced force. All right. So that's about resultant vector, though we have talked about all this in the previous classes also, but still I wanted to just refresh that so that we can move forward. All right, so now let's finally talk about Newton's laws. So this was the main aspect of today's class, and now we are going to begin with that. So Newton's first law. Okay, so here is Isaac Newton, Sir Isaac Newton, and this is the first law that he gave. Okay, I'll read it out to you first and then we'll quickly discuss it. Every object tends to remain in its uniform state of motion, that is at rest or constant velocity, unless an unbalanced external force is applied. Okay, you also call this as the law of inertia. You also call it as the law of inertia. Now what is the term inertia here? Okay, let's discuss that first. So this is how you define inertia. It is a property of any object or body to oppose a change in state of its motion. Okay, it is a property of a body to oppose the change in its state of motion. I will write that as well. Okay, a property or tendency, you may call it, okay, to oppose change in its state of motion, okay. So this is inertia, a property of a body, we may add, a property of a body to oppose change in its state of motion. Okay. So, for example, if you have a table lying in front of you, it is at rest, it will remain at rest unless you apply an unbalanced force on it. And even when you apply that, it will have a tendency to resist that. And you do feel inertia a lot of times. I can come up with n number of examples. So, for example, when you are sitting in a car and you suddenly press the accelerator, the car suddenly starts and you kind of feel a jerk. Okay. In what direction? In what direction? So, you tend to remain at rest. So, as soon as the car accelerates, you feel a jerk backwards. That is what inertia is. Imagine vice versa. Now, your car is moving at a very high speed and you suddenly apply brakes and the car suddenly stops. You feel a jerk forward, you feel a push forward. So, that is what inertia is. You were trying to move, even the vehicle stopped. So, you opposed that sudden change in motion. That is inertia. So, inertia can be majorly of two types: inertia of rest, or you can say the second type, inertia of motion. Inertia of rest or inertia of motion. Okay. So, when you were at rest and suddenly the car moved, you tried to stop, that was inertia of rest. And when you were moving with the car and the car suddenly stopped, you tried to still keep moving, that is inertia of motion. Okay. So, Newton came up with this idea that every object will tend to maintain its state of motion unless there is an unbalanced force. So, let me again go back to the previous slide. So, if this was 300 and this is 300, then there is no unbalanced force left. This 300 and this 300 is cancelling out, then your motion will not change. But if this is 300 and this is 200, then there is an unbalanced force of 100, and that is when your motion would change. Okay. So, that is what Newton said in his first law, that every object tends to remain in its uniform state of motion unless an unbalanced external force is applied. All right. Keep that in mind, write it down. This is also called the law of inertia. And what is inertia? A property of a body to oppose change in its state of motion, that is motion or rest. So, if something is at rest, it will try to be at rest. If something is in motion, then it will try to maintain that motion. One important thing here, that mass is a measure of inertia. Mass is a measure of inertia. Just qualitatively keep it in mind. Inertia is not something that you can measure. It does not have a unit. It is a property. But one thing that you can definitely say is that mass is a measure of inertia. We will talk about it, but understand it with a very small example, that if you have two tables, one is a hard wood table and the other is a plastic table. If you apply force on both of them, who has a tendency to oppose the change in its state of rest? Is it the heavier table or the lighter table? So, you would say the lighter table will move easily, but the heavier table you will need more effort. So, who is providing more inertia? So, you would say the heavier one. So, anything that is having more mass has also more tendency of inertia. So, keep that in mind as well. So, write down the Newton's first law, then we move forward. Alright. So, I hope you have paused down the video and copied it down. Now, this is the main law. If you ask me, out of the three Newton's laws, this is the main law that we have to talk about. Newton's second law. The net force acting on a body or a system is equal to the product of mass of the body and its acceleration. Now, can you understand this? That F is equals to ma. Can we understand this now? Definitely. See, we already have talked about it. Whenever you apply force, there is an associated acceleration. But how are the two related now? F is equals to ma. This is the main finding of Newton, you can call it like that, because this is the main law, Newton's second law. So, can you in a way also say that A is equals to F by m? Of course, yes. So, can you say that acceleration produced is proportional to the force? Now, imagine that table. When you are applying force, if you apply more force, you would expect more acceleration. At the same time, the acceleration is going to be inversely proportional to the mass. So if the table is heavy, then you don't expect that much of acceleration. But if it is lighter, then it will accelerate easily. So more mass means lesser acceleration for that given force. So this is the Newton's second law, that how force and acceleration are related. So the first law in a way defined force, that you need force if you wish to, change the state of motion. What did the first law do? It gave you the qualitative definition of force, that whenever you apply force, the state of motion changes. What is the second law doing? It is giving you the quantitative definition of force, that how much force do you need? You need more force if let's say you have to accelerate a heavier mass. You need more force if you need more acceleration. So can we say F is equals to ma? So force is what you apply and acceleration is what you get in response. Let's treat it like that. You apply a force, you get an acceleration. You apply a force, you get an acceleration. More mass, you get lesser acceleration. Less mass, you get more acceleration, because it can get affected easily. It has lesser inertia. So now let's take an example. If you have understood this whole triangle, F is equals to ma. So F is equals to ma, m is equals to F by a is equals to F by m. I am taking a very simple example very quickly. What is the example? Figure shows the forces acting on an object at rest. The mass of the object is 20 kilogram. Alright, so there's a 50 Newton forward and 10 Newton backward. So what is the net force? You would say 50 minus 10, that is 40 Newton, and this 40 should be equal to ma. Now m is 20 kilogram, so the acceleration turns out to be 2 meter per second square. So can you understand, by doing this you are achieving an acceleration of 2 meter per second square. Now calculate the resultant force. So the first part of the answer should be 40 Newton. We have already done that. Second part, what effect does this resultant force have on the object? Okay, so this object was at rest. And now you give it a force. What do you think is going to happen? You would say it will start, it will start its journey, it will start moving, so there will be motion. So you would say it will change its state of motion from rest to motion, or you can say it will start accelerating. All right, then what is the velocity of the object after 2 seconds? Okay, so now you know the acceleration thanks to F is equals to ma, that is Newton's second law. Now understand, acceleration is also delta v over delta t, if you remember the basic definition of acceleration. Okay, so acceleration is 2, delta v is going to be v minus 0. Why? Because initial velocity was 0 and the time of operation is 2 seconds. So these forces are applied for 2 seconds. So the value of v turns out to be 4 meter per second. So after 2 seconds, this will acquire a velocity of 4 meter per second. No problem here, no surprises here. Okay, so that's about Newton's second law, which is the main law that relates the force that you apply and the acceleration that is achieved, which is very important. Copy this down, then we will talk about the third law also, but before that we will take one more example. Alright, so let's take one more example. Suppose a car of mass 1250 kilogram crashes into a concrete wall. So it's not a very ideal state, but somehow the car crashes into the concrete wall. Okay, and the speed of the car is 7.2 meter per second just before it hits the wall. Calculate the average force on the car as it hits the wall if it takes 0.1 second for the car to come to a complete stop. So imagine the car collides with the wall and it stops within 0.1 seconds. Okay, so first let's do the A part. Acceleration is delta v over delta t. Now acceleration is delta v, that is 0 because the car stops, minus 7.2 divided by the time, that is 0.1. So this turns out to be 72 meter per second square with a negative sign. Negative sign is of course indicating deceleration. Of course this is deceleration, the car is stopping. Okay, and now if you talk about the force, so you use the formula F is equals to ma, because they are asking the average force, that is the force during this whole 0.1 second. So we can also call it as the mean force the car experiences, because even during that 0.1 second there might be a slight change in force. So we will call it as the average force for that duration. Okay, so mass is how much? Mass is how much? Mass is 1250. Let's do this calculation, times 72. Okay, so this turns out to be minus 90,000 Newton, or you can call it as minus 90 kilonewton. You can also call it as kilonewton. So you do understand how much is the force, and that is why it will destroy the whole car almost, because this force is way too much. On the contrary, what happens in the B part? So let's say the wall is, you know, like a little, you have a cushion there and you get more time to stop. You can imagine that maybe due to the airbags and everything and the suspension system of the car, okay, that you know, it takes more time. Though airbag does not affect the car's motion, it only saves the passenger. So airbag is not the right term to use, but still let's imagine because of the wall's you know, texture and everything, this happens. Okay, so now the acceleration will change. Let's call it delta v by delta t again, but this time delta v again is 0 minus 7.2, but the time is 0.4. So the answer is going to be 7.2 divided by 0.4. Okay, so this time it is only minus 18 meter per second square. So the force this time is going to be ma is 1250 times minus 18. Okay, so 1250 into 18, that should probably be 22,500. Okay, Newton, or you can call it as 22.5 kilonewton. So basically you can clearly see here that force has reduced by 4 times. So this force is 1/4 of this, because you got 4 times more time. So in the first case you stopped within 0.1 second, while in the second case you had more time. So since you had more time, that means, you know, force was less, acceleration was less. Okay, but again giving you a decent idea of how you have to do the numericals involving the Newton's second law. You just have to apply force is equals to mass into acceleration, and to calculate the acceleration you have to use the previous concepts of motion that we have learned very much in detail. Okay, copy this down, then we move forward. All right, next, Newton's third law. So this is, you would say, the first law defined force qualitatively. Second law gave you the quantitative definition of force, that force is mass times acceleration. Now what is the third law doing? Third law is giving you the nature of force. Third law is giving you the nature of force. Now understand this. No force in nature can be singular. All the forces in nature are always in pair. They are always two. Okay, let's understand how. First I will read it. For every action there is an equal and opposite reaction. So when I say action and reaction, they are like the two pair of forces. The pair of action and reaction acts on two different bodies simultaneously. Okay, so this might be a little surprising for you, but you know, sometimes it might not feel, but it is actually true that, you know, two bodies are applying equal and opposite force. I will take an example to explain this to you. So for example, you would say when you drop an apple, that is what the famous story for Newton is, that, you know, that apple fell. So let's imagine that apple is falling down. So you would say, or anyone would say, that earth is applying a force, let's say F, on the apple, and that's attracting the apple due to gravity. What if I tell you that the apple is also applying the same force on the earth? Can you imagine that? Force applied by the earth on the apple and the force applied by the apple on the earth is the same. But you would say, we can never imagine that earth is being pulled towards the apple. Why does that not happen? Because you do understand, acceleration is F by m. So even if the force is the same, mass of earth is way greater than mass of the apple, and that is why it gives rise to lesser acceleration. It's almost zero acceleration because mass of the earth is way too much. So you cannot imagine the earth will be attracted towards the apple, but the apple is attracted towards the earth, very much so. So can we say that they are equal and opposite force? Yes, but we cannot say they will have equal and opposite impact. The impact won't be equal. Forces are equal, but the acceleration won't be equal. Getting my point? So this is what Newton said, that all the forces in this nature exist in pair, that is, they are always equal and opposite. They act on two different bodies, and that too simultaneously. That too, you imagine this tug of war kind of a state where there is this person A and this person B. So A is pulling B and B is pulling A. Can you imagine? Both are applying equal force on each other. So the force is the same. Force applied on A by B is equal to the force applied by B on A, just the direction is opposite. But again, that can have different impacts because they can have different masses, but the force is going to be the same. Keep that in mind. Force is going to be the same, like if you have this ideal state where only A and B are interacting. So can we say that for every action there is an equal and opposite reaction? Yes. So you cannot have singular force. If you push a table, you are also experiencing a force backwards. In fact, this is the key. Now understand this with an example. How do you move forward? How do you move forward? How do you walk? You can't apply a force on yourself. What you have to do is you have to push the ground. You push the ground and you move forward. So what are you doing here? You push the ground gives you a reaction, and then you move. That is what Newton said. This is Newton's third law, that every action is going to have an equal and opposite reaction, and the two will always act on two different bodies simultaneously. So that gives you the nature of force. So every law has something to reveal about force. First law gives you the qualitative definition. Second law gives you the quantitative definition. Third law gives you the nature of force. Copy this down, then we move forward. Alright, in fact what I think is that this should be enough for this video. You first accommodate all this in your head, that what Newton's three laws are, and only then we should move forward with further concepts. But first, figure this out, how Newton's laws are working, what is force, what is the way you add force, and very importantly, if you don't know how to add vectors, go back to those videos where we have discussed scalars and vectors, how to deal with vectors. All that you should first understand and revise this all thoroughly. I will see you in the next video where we are going to talk about momentum, pressure, all these things, impulse. Going to be very new for you. It's going to be very exciting. I am very excited to talk about all these stuff. But today you just revise all this, and I will see you soon in the next video. That's all for today. Happy learning. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.